Friends, very good morning. We were dealing with the mechanism of sonication. Unlike microwave synthesizers, where microwaves interact with the molecules at the molecular level to produce heat energy. But however, in case of ultrasonication, it reacts with the medium. When it interacts with the medium, the bubbles are produced, which we call it as transient cavitation, when go on growing to the enormous size, and once it explodes, it gives enormous energy in the form of heat and pressure. Though it is transient, as it is in bulk when it is produced, it has its bulk effect. And this energy is utilized for the reaction. We have seen that ultrasound radiations have a very important role to play, and piezoelectricity invention paved the way for the inventions of ultrasonic waves. Various instruments were developed for the production of this ultrasound waves, and these are called as transducers. The first and foremost one was given by Francis Galton, Galton's whistle. It is named after him, where he used it to indicate that the different animals have different hearing wavelength. The humans can hear at a particular wavelength, sound wave, and the higher wavelengths can be heard by the other animals like dogs, cats, and so on and so forth. Other transducer is liquid transducer or liquid whistle, we call it as, and we have seen piezoelectric sandwich transducer, which produces ultra wave radiations, and magnetostrictive transducers. These are the few of the transducers for used for ultrasonic waves production. Further, there are various reactors developed. There is one probe reactor, probe ultrasonicator we call it as. It produces the ultrasound waves. The probe can be kept into the reaction medium, and the reaction can be carried out. There are various varieties of probe sonicators. This is the bulk probe sonicator, and these are bulk probes which are used for the cleaning purpose. We know that probe sonicators will have more effective ultrasonication than the bulk sonicators. By utilizing these sonicators, we can carry out the reaction. By the by, what type of reactions can sonochemistry accompanies? The applications of sonochemistry is very vast. It is applied in electronics industry for coating with metals. It is used in the therapy for diagnostic purpose. It is also used in the food industry. It finds its use in looking at the or finding out the any uh, problems in materials. It finds its use not only in synthesis but also in environmental pollutant detection. Now, the subject of today's discussion is synthetic applications of sonochemistry or ultrasonication. Organic synthesis can be accompanied by using sonochemistry. This organic synthesis can be achieved by ultrasonication by dissolving the reactants in a medium which is homogeneous nature, which come under the category of homogeneous sonochemistry. And if the reactants are in different phases, one will be in solid, another will be in liquid, then this comes under the category of heterogeneous sonochemistry. Homogeneous sonochemistry medium, whatever we use, can be an aqueous medium. Then this is called as aqueous homogeneous sonochemistry. If we use non-aqueous medium, then it is non-aqueous homogeneous sonochemistry. Heterogeneous sonochemistry includes phase transfer catalysis, the reactions with metals. When we use metals, that metals what we use are in the solid phase and the reactants are in the liquid phase, and they are in two different phases. That's why they come under the category of heterogeneous chemistry. And few of the condensation reactions are also the part of heterogeneous sonochemistry. Let us look into the homogeneous sonochemistry and its a few examples. In aqueous sonochemistry, water is used. Generally, water, when it is irradiated with ultrasound waves, it gives rise to corresponding radicals, H radical and OH radical. The OH radical can react with bromine to give water and bromine radical. The bromine radical which is formed is used to convert malic acid into fumaric acid under ultrasonication. This is the simplest of the examples of aqueous sonochemistry. I take benzoic acid, add into water, ultrasonicate it. Ultrasonication produces OH radicals which interacts with the benzoic acid to give corresponding ortho, meta or para substituted hydroxybenzoic acid. Sonochemistry not only useful in this, it is also used for reduction of metals. Ultrasound waves can reduce the metal ions like silver ions to give metal nanoparticles, and this is one of the best ways to generate nanoparticles. Let us look into the synthesis of heterocyclic drugs using ultrasonic waves under aqueous media. One of the drugs, cefendol A, has been synthesized by this method, in which 2-aminophenol was reacted with indole alpha keto acid in water, and it was irradiated with ultrasound waves for 180 minutes. It gave cefendol, which is a coumarin type of derivative, and the cefendol A is obtained in 81% yield. This is an indole alkaloid which is having anti-tumoral activity. And this reaction is the condensation reaction which occurs under ultrasonication in the absence of any catalyst. That is the salient feature of this cefendol synthesis using ultrasonication. Another heterocyclic drug we can deal, the synthesis of warfarin. S warfarin is a anticoagulant, as we know. We take 4-hydroxycoumarin and treat with alpha beta unsaturated ketone in water, and we are using a catalyst in 10 mole percent concentration. This is the chiral catalyst S, S diphenyl ethylene diamine. Diphenyl ethylene diamine. In this presence of this catalyst, when it is irradiated with ultrawaves for 10 hours at room temperature using acetic acid in 20 mole percent, it gave S warfarin in 61% yield with 99% enantiomeric excess. S warfarin is formed in 99% and another 1% is R warfarin. The optically pure warfarin is obtained using ultrasonification with 61% yield and having 99% enantiomeric excess. This can be accompanied by ultrasonication in aqueous medium, a simple method which occurs at very ambient reaction conditions. Now, you can appreciate the utility of ultrasonics in chemical synthesis, which are of having drug value. Beta amino carbonyl compounds formation by Manish reaction, a 3-component reaction, can also be accompanied by ultrasonication by using hydrotropic solutions. Here, a primary amine like aniline, a non-enolizable aldehyde like benzaldehyde, and an enolizable ketone like acetophenone is dissolved in water in which we are adding paratoluene sodium sulfonate in 50% concentration. This paratoluene sodium sulfonate is a hydrotope. What is this hydrotope? It is a non-missile forming substance. These are the set of compounds which do not have critical concentration above which self-aggregation can take place. By adding the sodium sulfonate of toluene in 50% concentration, it increases the solubility of the hydrophobic compounds like aniline, benzaldehyde and acetophenone. As it increases the solubilization of these hydrophobic compounds in aqueous phase, it hastens up the reaction and it undergo Manish reaction to give beta amino carbonyl compound. As it increases the solubilization of this non-hydrophobic components, what we use as reactants, it facilitates this 3-component coupling. Not only it increases the solubility of these hydrophobic compounds, but also it merges the low vapor pressure and it increases the viscosity of the medium in relative to water. By increasing this viscosity, it helps in formation of cavitation collapse in a stronger way during the compression cycle, and thus it hastens up the reaction such that the reaction could be completed in 0.75 hours. The yield achieved is 90% when it is carried out under ultrasonication, whereas in normal reaction condition heating method, the reaction for completion it took 5 hours and the yield was 75%. It not only reduces the time of reaction, which reduces the consumption of energy, and also it increases the yield. This is the salient feature of this ultrasonification reaction in Manish reaction. Non-aqueous solution can also be used when all the compounds are not soluble in aqueous solution like water, aqueous solvents. Then we have to go for non-aqueous solutions. That's why it comes under the category of non-aqueous sonochemistry. Generally, the solvents what we use should be non-reactant to ultrasound waves. N-alkyl quinolinium iodide, when it is treated with trichloromethyl acetate in the presence of acetonitrile as the solvent and irradiated with ultrasound waves, it gave 2 trichloromethyl and 4 trichloromethyl derivatives in 70 to 100% yield. The same quinolinium iodide, when it is treated with tertiary potassium tertiary butoxide and irradiated, it gives 2 tertiary butoxyl and derivative which got converted into corresponding quinolinone derivative. Quinolinium iodide, when it is treated with acetone in the presence of a base, it gives the corresponding substituted 2 substituted and 4 substituted derivative in 91 to 96% yield. The phosphorylation of this organic compound can be achieved in toluene as the solvent when it is heated at 90 degrees centigrade. The product can be achieved in 2 hours with 37% yield. Whereas under sonication, the reaction rate is enormous. Within 15%, 12% is converted into the product. In 30 minutes, 32%, and in 60 minutes, 67%, in 120 minutes, 82% of yield has been achieved under ultrasonication method. These are all the utility of sonochemistry in homogeneous medium, which may be aqueous or non-aqueous medium. In the coming presentation, let us deal with the heterogeneous sonochemistry. Till then, have a nice day. Thank you.